Hello everyone. We are students from Electronics and Communication Engineering Department at Gokaraju Rangaraju Institute of Engineering and Technology. Our project, a dual slot microstrip patch antenna with an Airgap for S-band applications. Contents are Introduction, Abstract, Antenna Design, Implementation, Results, Conclusion. Introduction. Vital part of contemporary communication systems. Antenna act as a bridge between electromagnetic waves in free space and electrical impulses in transmission lines. To efficiently transmit or receive electromagnetic waves within a particular frequency band, they are made in a variety of shapes and sizes. Among the many applications where antennas are essentially are broadcasting, RFID systems, satellite communications, wireless communications, and radar systems. An antenna's main purpose is to transmit electrical signals by converting them into electromagnetic waves, or the other way around, to receive electromagnetic waves and convert them into electrical signals. In this process, electrical energy is transformed into electromagnetic radiation energy and vice versa. Characteristics of antennas include gain, polarization, impedance, bandwidth, radiation pattern, and frequency response. The performance and appropriateness of an antenna for various applications are determined by these characteristics. To get the necessary performance characteristics, antenna designs entails optimizing these factors. Abstract. This paper describes the microchip patch antenna with a defective ground structure with dual slots operating at a 3 GHz frequency. The design consists of a FR4 lossy substrate of 1.5 mm thickness along with an air gap of 1 mm which is present between the partial ground and the patch. Dual slots are designed on the patch and simulation is carried out by the CST Studio Suite. For better impedance matching, lambda by 4 is used. The rectangular patch of the antenna is optimized with a rectangular slot to achieve the desired frequency, a gain of 3.45 dBA and a directivity of dBA. This research investigates critical characteristics including bandwidth, directivity, and radiation patterns in addition to the intended frequency and gain. Simulated data is collected for analysis and validation, and the performance of the antenna is recorded. This is our antenna design. Front view of the design. Parameters includes length of the patch, width of the patch, length of ground plane, width of the ground plane, length of slot length, right slot length. The proposed antenna in this project has four primary parts: ground plane, substrate, patch, and feed. Antenna construction frequently uses copper for the ground plane, patch, and feed because of its outstanding capacity to conduct electricity. Radiation and energy transmission are made more efficient by copper. The antenna is specifically designed to operate at a 3 GHz frequency. The internet layout is created and replicated by FR4 lossy with the dielectric constant ranging from 3.8 to 4.8. The dielectric constant of the substrate affects two electrical properties of the antenna: radiation efficiency and impedance matching. FR4 lossy is a commonly used substrate material since it is affordable and frequency, frequency dependent. Implementation. A popular software package called CST, Computer Simulation Technology, is mostly used for electromagnetic simulation, with particular applications in the design and analysis of antennas, RFID microwave components, and other high frequency electronic systems. When talking about CST technique, especially when it comes to the antenna design, analysis, and simulation. Results. The patch antenna has been optimized by parametric analysis. Parametric analysis has been applied to the variables PL, PW, and air gap. This is used to calculate the radiation pattern, gain, cross polarization of the antenna that will yield the best outcomes. Parametric analysis is the process of changing certain aspects of an antenna's design and evaluating how those modifications impact the antenna's performance. It helps antenna developers modify an antenna's characteristics to meet specific design goals and requirements. Parametric analysis of PW graph. Parametric analysis of PL. The length of the PL has been kept constant under parametric sweep in order to optimize for gain. The value of PL has been calculated using a range of 15 to 35 mm. As the value of PL changes, we get different values for the gain and return loss value. The graph shows that the lowest reflection coefficient occurs at PL equals to 19 mm. However, the antenna's gain is insufficient at that length. PL has been adjusted to 30 mm in order to increase gain while keeping the reflection coefficient at a respectably low minus 23 dB. Parametric analysis of air gap. By utilizing a parametric sweep from 0 to 0.4 mm, the hair parameter value is determined. The optimal hair parameter value to optimize gain and reflection coefficient is 0.2 mm. A 0.2 mm hair parameter setting results in a minus 18 dB reflection coefficient. This is S11 graph. S11 parameter for the suggested microstrip patch antenna between 2.5 and 3.5 GHz was the frequency range in which it was seen. The reflection coefficient of the final suggested antenna is lowest at 3 GHz. Minus 17.5 dB is the final return loss. The suggested antenna runs between 3 GHz and 3.5 GHz. This is the polar plot. Coming to the conclusion, a 3 GHz frequency operating rectangular microstrip patch antenna with a dual slot, impedance matching at 50 ohms, gain of 3.5 dBi, and cross polarization levels at minus 20 dB simulated. The addition of a dual slot resulted in a decrease in cross polarization and an increase in gain. Has a 90.8 degree angular breadth. Uses for the proposed antenna includes medical applications, satellite communications, radar systems, and unmatched aerial vehicles.